Dear students, in this video we are going to learn about single phase grid connected PV system. So these are the different blocks. We will try to discuss all the blocks, each and every, okay, one by one. So now this is a single phase grid system. Okay, let's discuss about these things. Okay, this is a single phase. So we have taken a voltage source. Okay, here we have maintained. In this one we can see here peak amplitude is 230 into 1.414, that is VRMS into root 2. Frequency is 50 Hz and sampling time I have taken 1080 e power minus 6. Okay. So this is my phase voltage. Okay. Now, so I want to calculate the current. Okay. How much is the current? Okay. Here you can see. So current obviously it will be flowing from this port A to grid. Okay. So you can see here plus and minus, but I have connected in to minus actually. So when I am going to measure the block, I will be placing -1. Okay, fine. So now how much is the voltage across this source? That is nothing but VA and that is Vm sine omega t. Actually this is Vm sine omega t, right? Okay, I will write here Vm sine omega t. Okay, so in case I want only sine omega t, then what shall I do? Divide this with Vm, right? So that is what I have tried to do it here. Okay, I try to divide this with 1 by 230 into root 2. Then I'm going to get only sine omega t. This is nothing but my sine omega t. Okay, so next here for this one, for this voltage, I want to calculate the RMS value also. This is my RMS value. Okay, so VSA RMS. Okay, this is what the name I have given, tag name. Okay, later on we are going to use this one in order to estimate how much power is actually injecting. Okay, for the power estimation, we'll see. Okay, so in this one, what and all we have done, one is we try to calculate the phase voltage, then we try to calculate the injected grid current, then we try to calculate the actual voltage. Okay, that is grid voltage. Then we try to calculate the vector, that is sine omega t unit vector, and this is the RMS value. Okay, fine. So coming to the another block, that is first we'll try to discuss the PV panel. Okay, so this is a PV panel. So I have used here two parallel and series. So four PV panels are connected in series. Such four panels, two strings I am going to connect in parallel. So total 4 to 8. 8 panels I have connected here. Okay. Panel specifications you can see here. Open circuit voltage is 46 and the voltage at maximum power point is 37.8. Okay. So now in case if I want to check the plot the parameters, then you can see here this will be my fixed. Here you can see array, so it is 1000 watt per meter square. This is fixed and I can able to calculate for this 45 and 25-degree temperature. Okay, sir, I don't want to do like this. I want to calculate as per the change in the irradiation. Then you can choose here array module 25 degrees centigrades. This is a standard. Okay, this is a standard. Okay, and these are the different irradiation. Sir, I don't want 500, I want 800. Okay, 800. I want here 600. Okay, you can take here 600. Further I want for 400. I want for 200. Okay, what, that's it. So this is a plot how you can able to get. So whatever I have collected here, that is for this 8 panels, these are the VA characteristics. Okay, for different irradiation, for different irradiation. This is my maximum power. Okay, here you can see these are my maximum power, maximum power, maximum power, maximum. These are my maximum power. Okay, once we have calculated this one, okay, once we are trying to find out the injected bleed current, then we are going to tally this. Okay, suppose you are going to say that, sir, I have my simulation is going to extract the maximum power, then how do you prove that one? So whatever the your whatever it may be, the power you are going to calculate, that should match this one. If it is going to match it, then you can say that yes, it is actually exactly it will not match, so because there will be some switching losses will be there. So it will, if it is near to it also, it's okay. Okay, this is how you can able to check your data. Fine. So this is about the PV. So what are the inputs for this one? Input will be your irradiation and temperature. What are the standard test condition? That is 25 degrees centigrade and 1000 watt per meter square irradiation. So here here you can change the irradiation. Okay, at time 2.5. Okay, at 2.5 seconds. So initial value is 1000. After 2.5 seconds, it is going to change from 1000 to 800. Okay, sampling time also you can give to 10 into e power minus 6. Okay, apply. Okay, done. So this is the standard temperature. Okay, and then okay, this is completely my boost converter. Okay, DC to DC converter we have discussed, right? So in this here we have discussed the DC to DC converter, DC to DC converter. Generally we are going to use boost converter. This depending upon the literature, they are going to use buck converter, boost converter, or buck boost converter. So here we have used boost converter. Okay, mostly we are going to use boost converter. Here we have used a MPPT technique, that is P and O I have used. Okay, so this is not required for you currently. Okay, so for this one we required voltage and current. So I have taken voltage and current. So this is your MPPT. Okay, so next is we are going to calculate the power. Okay, how we are going to calculate the power? Just voltage into current. That's it. Okay, that you are going to calculate the input power. This is your input power, or you can say power generated from the PV panel. Okay, so this will be acting as an input power for us. So we have given PPVA1 tag. Okay, we will be using this tag again. So this is my boost converter. These are my parameters. Okay, this is a boost converter. Okay, so we have discussed now PV panel and then the boost converter. Fine. After this boost converter, what is there? After boost converter, we are going to have an inverter. Okay, so one capacitor will be there. This is a DC link capacitor. Okay, most of you have drawn like this in exam. You have drawn simply the capacitor. It is not we should not give a capacitor, it should be a source. Okay, if you are going to draw only a inverter. Okay, so here we are using the this will be your DC link capacitor. Fine, this is your inverter, single phase inverter. Okay, in last videos we have designed the single phase inverter. Okay, so this will be your input, and here we are going to take the output. Here we are going to give the AC signal. Here we will be connecting the DC signal. Okay, fine, don't get confused with the rectifier and the inverter. Okay, fine. So in both the condition, DC will be given here only and AC will be given here only. Okay, that you can able to remember. This is a fixed one. Okay, so here I need to calculate the VDC voltage, right? So I need to maintain this at 400 volts, right? If you remember, here we have to maintain this VDC as 400 volts. Okay, because it is single phase. So this is my VDC. Okay, so I have given the name as VDC. Fine. So here PV panel is over and your inverter is over. This is one block. Fine. Now sinusoidal pulse width modulation. Okay, sinusoidal pulse width modulation. This is my repeating sequence. This is my sine wave, and this is in unidirectional one. We have used another negative sine signal also, right? So this is the one we are going to get. Then we are going to use a comparator, and then see this comparator generally uh, it depends upon the controller. Okay, at the end, what are the controller we are going to use? So in earlier case, we have discussed this as a greater than. So now here in this one, we are using it as a less than. So it you may change depending upon your whether your capacitor is charging or discharging. I will show you. Okay. So these are the signals again we are going to give. SA1 is a positive one, and this is a negative one, and the SA2 is a next one. Okay, SA2. This is a complementary switch. Okay. So for SA1, this is SA11 dash is complementary. As for SA2, SA21 dash is a complementary. If you check here, okay, here you can check. So this is our SA1, this is SA1 dash. Okay, these two are complementary signals and these two are complementary signals. Fine. So this is our frequency. So I try to maintain 5000 Hz frequency. Okay. Now coming to the reference. Okay. So what actually I want to maintain? I want to maintain a 400 volts DC voltage, right? This is my 400 volts. This is my reference voltage. This is the actual voltage, right? This is the actual voltage. You can check here. This is the VDC. This is the VDC. Okay, this VDC I would like to maintain it as 400 volts. Okay. So actually this I have masked here. Masked means like this you will get. This is called masking. Okay. So in masking you can able to click here. Okay, in this icon. Then it will open inside. Fine. So this is my actual voltage, and this is the calculated one. Then I am going to find out the error. Okay, that error I am going to give it to the voltage controller. Okay, generally it will be a PA controller. Okay, in general we are going to use it as a PA controller. Here what and all you have to take care. So here we have to take care of the discrete time and sampling time. You can able to use the same sampling time as which we have given in the this one. Okay, 10 into e power minus 6. Okay, here I have given P1 and I1 since I have masked these data, so that's why I have given here P1 and I1. Here actually P is 0.3, I is 5. Okay, that you can able to substitute here. So what are the changes you have to do? One is you change it to discrete time mode, then you have to give the sampling time, and then your P and I values apply. Okay, that's it. Okay, then here whatever may be the output, I consider this as current. Okay, as a current. Now I want to estimate the actual power production. Okay, since we are going to inject current into the grid, how much current is actually it is generating? How to calculate, sir? This is your uh, input, that is power generated from the PV divided by 230. So what is this, sir? VSA RMS. VSA RMS, that is this is the RMS value. RMS is the DC equivalent, right? DC equivalent voltage. So we have divided that power with the RMS value. Then we are going to get current, right? P is equal to VI. If I divide VI by uh, V, then what we are going to get? Only I, right? So here I am going to calculate the, this is my current. Okay, this is my current. This is the actual current. Now then I am going to compare these two. This is my reference current, this is actual current, right? This is my reference. Remember, till now all these things is DC only, right? Till now we have dealt with the DC only, that is your 400 volts, your VDC is a 400 volts, that is actual value. This is also DC component, this is also DC, this is also DC, all these are DC only. Okay, So now we have compared whatever the current is going to get. This is the actual current. This actual current, that is IA star. Now this DC component we are converting into AC component by multiplying with sine omega t. Okay, this is our sine omega t, right? VAU here. We try to calculate the unit temperature, right? So this one is this one. Okay. Now this is converting into AC. What is the actual AC? IA, which is a injected current. Okay, this current. Okay, we are comparing with this current, and then this is whatever may be the error, we are going to give it to the P controller. Here we can see maximum gain we have given, so that system will be in stable. Okay. Then here we have done the normalization. What is normalization process means? We are going to minus it with the actual voltage VNM. Okay. Then divided by VDC. This is nothing but all this complete thing is normalization process we are going to call. Then we are going to get a VA. Sir, why we have to do like this normalization process, sir? Because we want to get a reference voltage. We want to get a reference voltage which is of unit value or less than unit value. If you remember in our unipolar and bipolar, we have maintained 0.99. It has to vary from 0 to 0.99, right? So in order to get that in unit 1, so we have to do this normalization process. Fine. After this, we are going to get the V con A. This is nothing but your sine signal. That is this sine signal. Okay. Fine. So now, so actually what and all we have to calculate? We have to calculate the profile. What is a VDC voltage? Then how much power is in whether grid voltage and current are in phase or not. Here I have used -1 because current is injecting here, current is entering like this, but I have given it to the -1. Okay, that's why I have used here -1. Okay, if you change this polarity, then no need to give here minus. Okay, no need to give here minus. Okay, fine. Now here we are going to check whether voltage and current are in phase or not. Then here we are going to check the voltage is 400, VDC voltage is 400 or not. Then phase voltage we are going to check, and then we are going to check the THD here. Okay, so THD anyways you can able to do in two ways. Here whatever the data is there, voltage and current, so that we can able to log on to the workspace. Okay, so here I have given a VOP. Okay, uh, then this data we can be able to use, and we can use for the FFT analysis. Okay, fine. Next is how to calculate the efficiency and all. We'll try to do it. Okay, so now we will try to product this. Okay, already we are having VNM is already there, so we'll type directly product. Since this is a high gain unity, high power factor converter, so we need not require to uh, calculate the cos theta. Obviously, it will be nearly equal to 0.99 like that. So that's why you can take cos theta equal to 1. Okay. So here we need to take the RMS value, right? So check here where is the VRMS. Okay, VRMS is there. Apply. Okay. And then you can product it. Okay, and this is your power, right? This is your power. So this is RMS value, and IA RMS we required, right? So RMS value you can take here. Let me check this block. Okay, this one. Paste it. Let me take it as initial value as 10. Okay, apply. Okay. So here you can see it. I have given sampling time TS. So why sir you have given like this? So every time if suppose I'm going to change the sampling time, then everywhere I have to change. So instead of that one, simply write the TS like that, and you can see here, simply you can type here TS is equal to 10 into e power minus 6. That's it. Then whatever wherever TS is there, it will automatically take. Okay, it will automatically take it as 10 to e power minus 6. Fine. So this is my power. Actually, what I have done till now. So here I will take a gain also. Okay. No, gain is not required here since it is a single phase. Okay, I will maintain this as one itself. Okay, P is equal to VA cos phi. So V is a I is a cos phi. Almost we are trying to take it as a unity. Okay, because they are in phase. We will see it now. Okay, we will see it now. Okay, so we'll try to run. We'll try to connect this one, phase and neutral. Okay, we'll try to save it. This is your I will try to calculate for one value. Okay, you can do for the other values as a homework. So this is my response. You can check here. You can check here. So this is exactly in phase with the voltage. You can check here. Okay, you can check the. It is exactly in phase. Okay, it is exactly in phase with the voltage, grid voltage. Okay, try to calculate the power also. So this is actual power. Okay, it is coming around 2560. Okay, 2560 at STC, at standard testing condition. Okay, this is 2050. Okay. Okay, now see, RMS value is already, it is 230. It is a grid voltage. It will not change. Okay, so it is a fixed one. Now we will try to enter the data. What is the irradiations we have maintained here? Okay, we'll check each and every one. Okay, before this you try to do the THD analysis also, FFT analysis. See, wherever your signal is stable, that you choose. Okay, here at 1 or up to from 0.5 to before 2.5, it is stable. Okay, here whatever the data is there, that is 1000 irradiations, 25-degree temperature, right? So now IS is there. Okay, okay, this data I will take, and up to 10,000 I will try to calculate and display. Here you can check THD is 3.14. Okay, and lower order harmonics, that is the total THD should be less than 5%, and your lower order harmonics like third, fifth, seventh, these things should be less than 4%. So both the things here it is satisfying, that is overall is 5%, less than 5%, and here you can see the lower order harmonics are less than 4%, that is less than 1.6% almost. Okay, so both the conditions are satisfying, so the response is very good. Okay, now that is THD profile is good, you can say. Okay, and then we are going to calculate, this is already I told you that this is the maximum value. Now we want to calculate the actual power. Okay, so then how to calculate the actual power? 230 into so how much is this one? 15.73. Okay, divided by 1.414. Okay, 25258. Okay, this is your output power. Now we'll try to put all the data. So irradiation is 1000 and temperature is 25, and PV generated power. Okay, PV generated power. How to calculate this one, sir? So here you will be having PV generated power. So this is the product. Okay, here it is a PV generated power. How much it is? 2600. Okay, so we'll take it as a 2600. 2600. Injected current. Okay, injected current. How much current it is? Okay, here we can see injected current is 15.73. 15.73. We can write here injected current, or we can even divide it by 1.414. You directly calculate it better. 15.73 divided by 1.41. 0.414. Okay, so that is 11.12. Okay, 11.12. 11.12. Okay, then THD. How much is the THD? THD, how much we have got? It is 3.14. 3.14. Output power, how much we have got? Okay, so this one into 230. 2558. 2558. So efficiency, that is output by input, simply. Okay, output by input. This is our output divided by input, 2600. So 98.4 is our 98.4. This is our efficiency. That's it. Okay, this is our efficiency. So this is how you can able to calculate. Okay, hope this video is hope this video clarify all your doubts. Still, if you are having, you can contact me. Okay, so okay, hope I have covered all the things. Okay, you can play these videos in 1.5 or 2x speed. Okay, right. So this is about the single experiment 4. Okay, so that is single phase two-stage grid connected system. Okay, I try to tell you this thing, right? So in case if I'm going to change this one, okay, we have not checked all the details also. Wait. So here you can check measurement block VDC. Okay, almost it is constant. Here we try to change the irradiation change. Okay, yet it has it has stabilized to 400 volts. You can check here. The maximum variation is less than 2.5%. Okay, so our response is very good. And phase voltage, here actually phase voltage we have given high gain, so that's why you cannot expect you can expect like this only. If you try to minimize the gain value, P value, then you can expect a good response here. Okay, and finally yeah, we'll try to change these things, then we'll see what will happen. Okay, I'm trying to change these values. I will try to see. Okay, then you can see here measurement block. You can see here capacitor is constantly discharging and discharging. It is keep on charging. Okay, sometimes you are going to see like this. Okay, sometimes you are going to see like this, that it will completely drop out. Okay, in such conditions you can change these things. Okay, when you are designing, try to change this one. Okay, try to change this one. Let's, then you can observe your voltage. Okay, right. Okay, hope this is informative to you. Okay, meet you in the next experiment. Okay, in the next video.